Good morning, abstract algebra students. It's good to be back for another problem-solving session in advance of tomorrow's quiz. So tomorrow, the order of the day is going to be to talk about cyclic groups. And as we talked about in class this week, cyclic groups are everybody's best friend. They are everywhere you want them to be. Everything you want to be true about all groups is actually true about cyclic groups. And one of the main themes for this semester is going to be the extent to which the cyclic groups actually form the foundation, they form the building blocks of all finite abelian groups. So that's actually the theorem that we're going to spend all semester building our way towards. And the theorem says something along the lines of every finite abelian group can be understood as a product of building blocks of finite cyclic groups. And so understanding the cyclic groups and understanding them well actually gets us a long way down the road to understanding all of the finite abelian groups. Of course, the non-abelian groups are a much different story, but the finite abelian groups are completely classified by their order and use the finite cyclic groups as their building blocks. So because the cyclic groups are so nice, a lot of the properties that we're going to see are true of them are things that we want to be true later on of other groups, but sometimes are and sometimes are not. So let's take a look at the agenda for what I'm hoping to do today. And if you're not my current student and you're watching this, you can contribute questions via the Twitch chat. If you're my current student, feel free to drop questions into the Slack Doctor's Office channel, and I'll be able to respond to those as we go along. So what are we up to today? First thing I want to do is go through a quick exercise that uses the concept, the definition of order, once again, the order of an element. And so that exercise will convince us that the order of an element is the same as the order of any of its conjugates. And then after that, I want us to look at a piece of what I called in class this week, the fantastic theorem about cyclic groups. And the piece is that every divisor of the order of a finite cyclic group has an element of that order in the group, and vice versa. So this important piece of the fantastic theorem, we're going to look at a proof of it and why it works. And then from there, jump off into a discussion on request from one of you on the Euler phi function. So just a little bit more detail, a couple more examples on how to use the Euler phi function and what does it actually tell us that we care about in abstract algebra. We'll look at another proof of a property about cyclic groups, and that property is that the property of being cyclic is inherited from parent to child. So any subgroup, if I'm a subgroup inside of a cyclic group, then that means that I'm going to be cyclic as well. This is an example of a kind of inheritance property that also is true, for example, of abelian groups. Inside of an abelian group, if I'm a subgroup, then I also must be abelian. That's a little bit easier to see why it's true than the cyclic example. So hopefully we'll get a chance to talk about the proof of why every subgroup of a cyclic group is actually also cyclic. And then finally, we'll look at the additive group of integers, z mod p, where p is a prime number, and prove that that group is what we call simple. It has no subgroups that are interesting. The only subgroups that it has are the same subgroups that every group has, namely the trivial subgroup consisting only of the identity element and the whole group itself. And so if my group is z mod p, then those are the only subgroups that it has. There are no others that are intermediate. So some of the exercises that we're looking at today are taken out of our Judson online textbook, so we may be referring to this once in a while. But some of them are not, and some of them are just proofs that I sort of decided that would be good to do. But what I want to do is I want to start, because it's going to give us a little chance to talk about Euler phi function straight out of the chute. I want to talk about the problem number 8 on this list right here, which invites us to list all of the cyclic subgroups of the group U30. So let's start with there, because again, this is going to give us some Euler phi function practice. So U30. Recall, first of all, that U30 is going to be the set of all numbers from 1 up to 29, such that that number is relatively prime to 30. So the elements of U30, this is the multiplicative group with multiplication mod 30. Right? This is a multiplicative group, and its elements are only going to be able to be those residues mod 30 which are invertible, which we can multiply by some other residue mod 30 and get the multiplicative identity, which is 1. And so it's a basic principle of number theory. It's the part of the Euclidean algorithm that we're going to talk more about later on in this video. That, oops, I didn't finish this sentence up here, my apologies. That those residues mod 30 that are invertible, multiplicatively invertible, are those that are relatively prime to 30, whose greatest common divisor with 30 is equal to 1. Okay. So the first thing that we might ask is how many elements? What is the order of this group? So, well, the number of elements is going to be the same thing as the number of k's between 1 and 30, exclusive of 30, that are relatively prime to 30. And that's, by its very definition, exactly what the Euler totient function, or the Euler 5 function, was sort of designed, was defined to count for us. Euler 5 function of 30. So let's use this as an opportunity to just review how to compute the value of an Euler 5 function. If I want to know what is phi of 30, what I want to do is two things. I want to make use of the multiplicativity of the Euler 5 function. And the multiplicativity property of the Euler 5 function says that phi of x times y is equal to phi of x times phi of y, but not always. Only when x and y are relatively prime. Relatively prime. So I want to use that property. And then I also want to use the formula for the Euler 5 function that says if p is a prime, then the Euler 5 function of the kth power of that prime can be explicitly computed as p to the k minus 1 times p minus 1. So I want to be able to use both of those facts to compute the value of an Euler 5 function, like Euler 5 function of 30. And so my general workflow is I want to use the multiplicativity property first, and then use this formula second at the end of the day. So before I can use the multiplicativity property, I need to understand how the number 30 in this case can be factored into a product of relatively prime numbers. For a number like 30, that doesn't take too much thinking. For larger numbers, that might take a little bit more thinking. And in those cases, we would probably have to go through the whole process of finding the prime factorization of that number. Let's just do it as a prime factorization problem right off the bat here, just so we don't have to mince words. So the number 30 has as a prime factorization, well, 30 is 6 times 5, which is 2 times 3 times 5, right? So that would then be the prime factorization for 30. So always, my recommendation, anytime you're evaluating a Euler 5 function, is first find the prime factorization of that number. So 2 times 3 times 5. And why that helps is that we know for sure that all of the different prime power factors that make up the prime factorization of this integer are not only prime, they're therefore relatively prime one to each other. Right? And so 2 is relatively prime to 3, 2 is relatively prime to 5, 3 is relatively prime to 5. Therefore, now I can use this multiplicativity property to break apart this Euler 5 function. Phi of 2 times 3 times 5 is therefore going to be equal to phi of 2 times phi of 3 times phi of 5. Phi of 2, phi of 3, phi of 5. Right? So that's what the multiplicativity property does for us. Right? And the key to using it is finding the prime power factorization of our number first. Now we can use this formula that says that the Euler 5 function of any prime power is just the one fewer power of that same prime times one less. So one less power times one less than the prime. One way to think about that. And therefore, phi of 2, since 2 is a prime number, is equal to 2 to the 1 minus 1 times 2 minus 1. Phi of 3 is 3 to the 1 minus 1 times 3 minus 1. Phi of 5 is 5 to the 1 minus 1 times 5 minus 1. Again, those 1s are coming from the fact that there's a first power on all those primes up there. So I do all of those multiplications. All of my 1 minus 1 powers are just going to turn out to be 0 powers, and so they're just 1s and they vanish. So I have 2 minus 1 times 3 minus 1 times 5 minus 1. That's 1 times 2 times 4. That's going to be 8. So the answer to the question, how many elements are there in U30, is that there's 8 elements. Cool. So every evaluation of an Euler phi function, we can put into this sort of general strategy for how to do it. Find the prime factorization, then use multiplicativity to break apart the Euler phi function over the prime powers from that factorization, and then use the 1 less power times 1 less than the prime formula to compute each of the factors in your Euler phi function. Okay, so now we're ready to talk about the subgroups of U30. This is also sort of secretly a problem that I chose because I like talking about subgroups. Let me get my browser out of the way here for a moment. And now we can start thinking about, now that I understand that there are 8 elements, and we'll take a moment and list them here, how can I figure out what the subgroups are? And not only that, what are the cyclic subgroups? The fact that we're asking about cyclic subgroups actually makes this a little bit simpler question, because it doesn't require us to grapple with the question, is U30 a cyclic group? So we'll be able to kick that can down the road a little bit. All right, so the cyclic subgroups of U30. Let's figure out what are the elements of U30 first. What are all of the numbers less than 30 that are relatively prime to 30? So of course 1 is always going to be an element. 1 is relatively prime to 30. And 29 likewise. 29 is relatively prime to 30. Since 30 has 2s, 3s, and 5s in it, 2, 3, and 4, and 5, and 6 are not going to be a part of my group, but 7 will. And then after 7, 8's out, 9's out, 10 is out, 11 is in, 12 is out, 13 is in, 14 is out, 15 is out, 16 is out, 17 is in, 18 is out, 19 is in, 20 is out, 21 is out, 22 is out, 23 is in, 24 is out, 25 is out, 26 is out, 27 is out, 28 is out. We have all 8 of our elements right here. So here are my 8 elements that are that make up U30. If I want to know what the cyclic subgroups of U30 are, remember what a cyclic subgroup is. A cyclic subgroup is nothing more than the set of all powers. And so if I take one of my elements, like 1, and I find the cyclic subgroup generated by 1, right? That's just going to consist of 1, 1 times 1, 1 times 1 times 1, all of these multiplications happening mod 30, of course. Right? But no matter how many times I multiply 1 by itself, mod 30, I'm going to get just 1. 7, on the other hand, if I multiply 7 times 7, I get 49, which is 19, mod 30. I multiply 7 times 7 times 7, which I get 343. If I take 343 mod 30, I get 13. If I multiply that by one more 7, I get 2,401, but 2,401 is 1 mod 30. So the cyclic subgroup generated by 7 has these 4 elements in it. And it turns out, Remember, the cyclic subgroup generated by any element is also the same thing as the cyclic subgroup generated by its inverse. We proved that in class just yesterday. And so whatever the inverse of 7 is, mod 30, it will also be a generator for this 4-element cyclic subgroup. So what is the inverse of 7? Is it 19? It's not 19, because 7 times 19 is not equal to 1, mod 30. 7 times 13 is 91 as an integer, which is equal to 1, mod 30. And therefore, 7 and 13, because they're inverses, they're both generators for this cyclic subgroup. Either one of them can be a generator. And then we could go on and keep listing all the others as well. The cyclic subgroup generated by 19 is just 1 and 19. The cyclic subgroup generated by 11 is just 1 and 11. What are the other numbers we're missing here? The cyclic subgroup generated by 13. No, we already have 13. We took care of it. How about 23? So 23 times 23, that's going to be 529. And so mod, what is that going to be, mod 30? That's going to be 19, mod 30. Oh. And then we would multiply that by 23 again and get another number, multiply it by 23 again and get another number, etc., etc., etc. So let me pause on this 23 example. What's the cyclic subgroup generated by 23? Because I want to ask a related question before we finish talking about the Euler 5 function. Let's also remember what the other sort of abstract algebra meaning for the Euler 5 function ends up being. So let me, let me make some space here. So the Euler 5 function counts the number of natural numbers less than n that are relatively prime to n on the one hand. But that means that it does two things for us. It tells me the order of un, how many elements there are in my U group. But it also tells me the number of generators of Zn. So the Euler 5 function has that dual purpose for us. It can tell me how many elements there are in the multiplicative group mod n. It can also tell me the number of generators there are in the additive group mod n. Both of those things are equal to the Euler 5 function of n. So if we were to ask the question, well, let me actually add to this. The number of generators for the additive cyclic group of order 30 is also the same thing as the number of elements of order 30 in any cyclic group that has elements of order 30. Right, so if my cyclic group has any element of order 30 at all, it will have phi of 30, or it will have 8 of them, because each one of them is going to have a cyclic subgroup that, each one of them is going to generate a cyclic subgroup that is the same as the additive group Z30. Okay, so if we look at, for example, U30, we might ask a question like, is U30 itself a cyclic group? Is there any one of these numbers that is capable of generating the entirety of the group? And so let's think about 23. What is 23 going to be able to do for me here? What can it generate? Well, 23 multiplied by itself, we decided was congruent to 19. And then if I multiply that by 23 again, 19 times 23, then mod 30, that's going to give me 17. And then if I multiply that by 30 one more time, that's going to bring me back to 1. And so the cyclic subgroup generated by 23 is 1, 23, 19, and 17. And again, because 17 is a generator for this group, so is its multiplicative inverse, 23. So actually what I want to do with this information, 17. We know now what all of the cyclic subgroups of this is. I think the one I left off here is the cyclic subgroup generated by 29. Which I think has just 1 and 29. Let me double check that. Is 29 an element of order 2? 29 times 29 is 841, and that is equal to 1 mod 30. Okay, so let's just take this opportunity to conclude this example and take all these subgroups and place them into a subgroup lattice with a lattice of cyclic subgroups of U30. And all that means is I'm going to take these various cyclic subgroups and show how they are contained one in another. So I'll take the smallest one, I'll put it at the bottom of my diagram, and then this subgroup 1 is contained in all of these other subgroups, but in particular it's contained in the cyclic subgroup generated by 11, the cyclic subgroup generated by 19, and the cyclic subgroup generated by 29. 119, 129, 111. And I'll just draw little lines here. You can think of them as arrows if you like. That are basically just they're subset arrows, really. But we can show that they're more than that. Because a subgroup of a subgroup is still a subgroup. We can think of these as being subgroup arrows. So this one is a subgroup of this, and it's a subgroup of that, and it's a subgroup of that, and so on and so on. But then 1, 19 is also a subgroup of this one, the subgroup generated by 7. It's also a subgroup of this one, the subgroup generated by 23. So coming up a little further here, we'll put those two, 1, 7, 19, 13, as well as 1, 23, 19, 17. And 119 is a subgroup in both of those. And then I suppose we have the whole group up here on the top. 1, 7, 11, 13, 17, 19, 23, 29. And then, therefore, we get all the way up to the very top. But this kind of a diagram is what we call a lattice of subgroups. And sometimes the lattice of subgroups can be a powerful tool for distinguishing different groups one from another. Because two groups that are the same are going to have a lattice of subgroups that looks the same, right? We may call the subgroups different names because the elements have different names, if the groups might be superficially different. But if the lattices themselves are the same, then that means that the groups, the lattices themselves will be the same, provided that the groups are the same. And I suppose I would need here to also draw in some arrows from these up to the top. But you get the idea, right? That one way of arranging all the information that we might have about subgroups is just by using a diagram like this one. So this is the lattice of cyclic subgroups of U30. But notably, we listed all of the 1, 2, 3, 4, 5, 6, 7, 8, all of the different cyclic subgroups generated by the various 8 elements of U30, and none of them had more than 4 elements in it, right? The biggest cyclic subgroups we got were the ones generated by 7 and 13, and the ones generated by 17 and 23. None of these cyclic subgroups gave me the entire group. And therefore, we can conclude, based on now an exhaustive list of the cyclic subgroups of all generated by all different elements in my group, we can conclude that Z30 is not cyclic. Or sorry, U30 is not cyclic. U30 is not cyclic. Because none of its elements by itself can generate the entire group. So I'm going to take a quick, just a 15 or 20 second pause here. This was our sort of initial exposure here to using the Euler phi function a little bit to do computations and think about how many elements there are of a certain order. And then we use that to list the cyclic subgroups of U30 and then also come up with a subgroup lattice for it. So when we turn the corner here, I want to start looking at how to use the principles we've learned in this chapter in the sort of more proof-oriented context. So we want to look at some of the elements of our fantastic theorem and why it is that they're true. So quick 20-second pause, and then we'll come back after that. So one of the best things in the world about cyclic groups is that the divisibility properties of their order, when they're finite, the divisibility properties of that order tell us everything that we need to know and will guarantee for us that a lot of things that we want to be true for cyclic groups indeed are true. So in our class just yesterday, I presented what I call the sort of the fantastic theorem about cyclic groups. And just to take a quick look back at that before we move on, what were some of the things that the fantastic theorem said for us? The fantastic theorem, in my rendition, is that if G is a finite cyclic group, and its order is called n, then for every divisor of n, we can find an element in the group that has that order. So if my cyclic group has order 120, then I know for sure that that group is going to have an element of order 2, and of order 3, and of order 4, and of order 6, and of order 10, and of order 12, and of order 24, and of order 48, and of order 60, right? So all of these divisors, I guess 48 doesn't work, but 60 does. Every single divisor of the order of a cyclic group, there will be an element of that order. And therefore, a subgroup of that order, because that element of that order is going to generate a cyclic subgroup of the order equal to the order of the element. So every single divisor is represented as the order of at least one element inside of that group. And not only that, the Euler phi function then tells us more specifically how many elements of order k exist in that group for every divisor k of n. The other piece of the fantastic theorem is that for cyclic groups, when L does not divide n, anything which is not a divisor of the order, there is no element of that order in the group. So what I want to do is, actually let's jump directly into this part of the fantastic theorem where we're going to look at a proof for the first assertion that's here. The assertion that for every divisor k of n that you give me, I can give you an element of order k. So why should this thing be true? We're going to write out our napkin version of this, and then we're going to look at the, try to write up a more formal version for this proof. So I just got to adjust my screen here real quick. So one of the downfalls of teaching in a widescreen classroom is then coming home and having to do a live stream that's not on widescreen. Just pull that, adjust it, make one more little adjustment here because now everything has gotten out of whack. Okay, so what is the thing that we're about to prove, this component of the fantastic theorem? Well, it's going to sound like this. Let G be a cyclic group of order n. Then there exists an element of order k in my group if and only if k is a divisor of n. So you give me a divisor, I can give you an element whose order is equal to that divisor. So just let's do a concrete example first before we start to try to look at the more general case. So if G is cyclic and has order, I don't know, let's say 500. Okay, so G is a cyclic group that has 500 elements in it. Then let's think about what that means. By definition of cyclic, we know for sure that there's going to be a generator. For my group. That's what cyclic means, that there's one element whose set of powers is going to give me all the elements in my group. And so if I call that generator A, then I know what the elements in my group are going to look like. G is going to consist of an identity element, which is to be thought of as the 0th power of A. Let me get some preemptive color coding here. Right. The 0th power. And then I'm going to have the first power of a, that is to say a itself. I'm going to have the second power of a, that's a squared. I'm going to have the third power of a, and so on and so on and so on. And the highest power of a that I have that's going to be distinct from all the others that I've listed is going to be the 499th power of a. So a to the 1, a to the 2, a to the 3, all the way up to a to the 499. And if I were to multiply by one more power of a, once I got to this highest exponent, I would get a to the power 500. But the order of a is 500. And therefore, a to the power 500 is going to be equal to the identity once again. So just to remind ourselves of that fact, let me kind of add that observation here at the end. A to the power 500 is going to get me back to the identity. And so the picture, again, is that like these powers of A are just the points arrayed around a 500-hour clock. Remember how I like to say that every single finite cyclic group can be thought of as just being elements arrayed around the face of a clock, and the arithmetic just being the adding of hours on that clock. A to the 499 is going to be the last one here next to a to the 0, a to the 498. And so forth, right? So that's what my group is going to look like. And so if you were to ask me to find, let's say, find an element of order, I don't know, find an element of order 25 in this group. Where am I going to find it? Well, we can answer that question by making the comparison, making explicit the comparison. When I say that every finite cyclic group can be thought of as a group around a clock, additive group around a clock, what I really mean is that we can draw a comparison between G and the additive group Z500. Because what are the elements of Z500 going to look like? They're going to be these additive residues, mod 500, starting with 0, and continuing with 1, and continuing with 2, and so on and so forth, and up to 499. But as soon as I add one more to 499, I'm going to get back around to 0, mod 500. And so Z500 can also be thought of as a clock group with just the numbers 0, 1, 2, 3 going around the clock, coming up to 498. 499. And then I add one more hour, I get back to 0. Right? So rather than starting by trying to find an element of order 25 in my abstract cyclic group of order 500, I'm instead going to ask, how do I find an element of order 25 in the additive group Z500? Answer that simpler question first, and then we'll take that question back to the abstract context. So in Z500, the additive group mod 500, how do I find an element of order 25? Well, I would just be looking for an element x that when I add it to itself 25 times, in other words, when I multiply it by 25, that the result is going to be 0 mod 500. So I need a number x which, when I multiply it by 25, the result is a multiple of 500. Well, we can at least get one solution for this just by doing x equals 500 divided by 25 as integers. 500 divided by 25 is 20. And so, of course, we can check that 20 times 25 does indeed give me 0 mod 500, because it gives me as an integer 500. So I want to stress here that this is an example of a solution to this congruence equation. It's not the only solution to this congruence equation, probably, for reasons we'll talk about in a second. But at least we know that in Z mod 500, the element 20 is going to have order 25. So wherever that happens to lie here, maybe here it is, the element number 20. This element has order 25. But then if we want to bring this back to the abstract group G, what element would we be talking about? Well, the sameness relationship that I've set up here between G and Z500 is just the relationship of taking the exponent which we've placed on our generator and using that as the integer the residue class of integers mod 500 that were being represented down here. So, as you might expect, if I'm looking at the number 20 in the group Z mod 500 as being an element of order 25 in this group, then the element to which it corresponds in the abstract case is going to be an element of order 25 in the abstract group. And that element is just going to be that power of A which has as its exponent the number 20. So, if I want an element in G, the element I want is A to the power 20. And just to convince ourselves of that fact, let's verify that if I take A to the power 20 and I take its 25th power, what am I going to get? Well, the power of a power, just by general properties of exponents, we're going to multiply 20 times 25. But 20 times 25 is 500. And A to the power 500, by our assumption over here, A was the generator of this group, so its 500th power is equal to the identity. And therefore, we at least know that the order of A is a factor of 500. But we also know, the order of A to the 20 is a factor of 25. But we can check that no smaller factor of 25, such as 1 or 5, will make A to the 20 to that power equal to the identity. A to the 20 to the power 1 is not the identity. A to the 20 to the power 5 is A to the 100, but that's not the identity either. Therefore, 500 must be the order of the element A. So that's how we knew that the divisibility was enough. It was this step down here that convinced me that it was exactly because 25 was a divisor of 500 that I was able to solve this congruence so simply. To find me an example of an element of order 25 inside of Z500. And because Z500 had it, so did my abstract cyclic group of order 500. So that's the main idea. If you gave me a number down here which was not a divisor of 500, let's just take a quick look and see how the game might have changed for us. So if I wanted to find, instead of an element of order 25, maybe I wanted to find an element of order, 7. If I want to find an element of order 7, I would first go looking for it, again, in my concrete group of integers, additive group of integers mod 500. So in Z500, we would have to solve the congruence 7 times x is congruent to 0 mod 500. And of course, the problem with trying to solve that congruence, let me shrink my browser again a little bit here. The problem with trying to solve that congruence is that because 7 is not a factor of 500, in fact, because they're relatively prime, there's no way of multiplying 7 by x to make it a multiple of 500 unless x is already a multiple of 500. So only x equals 0 will satisfy this equation, but 0 is not an element of order 7, it's the identity, and so its order is 1. Okay. So we can't do it. There is no element of order 7 in Z mod 500, and therefore there's no element of order 500 in our abstract cyclic group either. Okay, so with that backdrop, let's see if we can discover a way to prove this fantastic theorem. There exists an element G of order k if and only if k divides n. So I want to think about this in two ways. Since we have an if and only if statement, that means that we really have two burdens of proof. We have the burden of proof going from right to left. So we assume that k divides n. And then we want to prove that there exists an element of order k. So that's going that direction. But then we would also have a burden of proof to show that the other direction holds, okay, which would be assume that there exists an element of order k, and then we want to prove that k divides n. So we really have to do both of those things at the end of the day. And so because I know that, I'm going to highlight that as part of my overall proof structure and strategy in my written up proof. So let me get that on the page first. We must show. Well, here's often how mathematicians, when they're writing up a proof of an if and only if biconditional, is that they'll just sort of split it up by saying forward implication. So they'll section their proof into two sections, a forward implication section and a, whoops, I'm using the wrong copy-paste keys here, a forward implication and a reverse implication, or a backwards implication, depending on how you want to call it, right? So I'm going to preemptively sort of set up those two sections in my proof. Forward implication section and a reverse implication section. Where did, oh, I'm typing in the wrong place. Haha. Let me get to where I actually want to be here. Sorry. Yet again, a problem of live streaming something real time. All right, so I'll have a forward implication section and I'll have a reverse implication section. And I want some considerable amount of space in between them. So let's actually start. I kind of want to start on my napkin with this reverse implication up here. Assume k divides n, and I want to prove that there exists an element of order k, because that's the example like the one that we already did, right? So if k divides n on my napkin, what does that mean? That means that n is a multiple of k. So n equals kj for some integer j, right? So just to keep our feet planted here, the concrete example that we worked on in the beginning was where n was equal to 500, and where the element order I was looking for was 25. So order of group and order of the element. And what we decided, what we ended up doing, was we found our element, call it g, we found it by dividing 500 divided by 25. Right? And it was because we could do that division that we could find such an element. Well, what role is this 20 playing over here? This 20 is exactly the quotient of n by k. And in this equation, the quotient of n by k would be the integer j. So this 20 here is evidently going to be the role of my j. And so on my napkin, I'm going to kind of ask, is j my desired element? And of course the answer is pretty much, but not exactly, right? Because this division process that I did over here, I can't really call that division an element of a group, unless I call it an element of the group Z mod n. So I'm just going to remind myself in this calculation here that in Z mod n, this element is an element of the desired order. So then I just need to translate using the translation that we talked about before, which is that the integers in the integers mod n, right, relate to the cyclic group of order n just by being the exponents on the generator, right? And so what we want is we want j as an exponent on the generator. Right, because that's going to get me to the abstract group context that we're looking for. And so now we'll ask, is a to the j my element that I'm looking for? So does a to the j have order k? Well, a to the j to the power k is going to equal a to the j times k. That's going to be a to the n. But since a is a generator, a to the n is the identity. Since a is a generator, right? And therefore, the order of a to the j divides k. It's a factor of k. But it can't be any less than k, because if I take a lesser power of a to the j, so a to the j to the l, for L less than k, that's not going to be equal to the identity, because it's going to be a power of a which is less than the nth power of a, and only the nth power of a comes back around to the identity, no lesser power, because the order of a is equal to n. So here are my napkin scribbles. Let me turn those into a proof of what will be our reverse implication, right? Because we're starting by assuming that k divides n, and then proving that there exists an element of order k. So we'll signal to the reader that what we're doing here is proving in a direct proof the reverse implication. So assume, or let's say it this way, let k mid n. So let k be a divisor of n, be arbitrarily chosen. We will show that there exists an element of order k in the group G. All right, so again, I've introduced k so that there's no surprise when it comes along, and I've stated my burden of proof. We're going to show that there exists an element of order k, and therefore we'll show by direct proof that the reverse implication is true. All right, so how did we do it? We constructed, right up here, I constructed my element, a to the power j. And so we'll use the word let again. Let g equal a to the power k. Sorry, a to the power j. But an astute observer would recognize that right away, immediately, I have a surprise symbol. I haven't told my reader what in the world a means. Right? So what is a? A is supposed to be a generator for my cyclic group. So I should say that right at the beginning. At the very least, I should say it at the beginning of my reverse implication, but maybe I should say it at the beginning of my proof. So since G is a cyclic group, there exists, by definition of cyclic group, there exists a generator, A in G. Right? So we introduce the generator A by making an appeal to the definition of cyclic. Let's also make the observation, observe, that the order of A is going to be n by definition, as well, by definition of cyclic. Right? So at the very beginning of the proof now, we're reminding the reader, cyclic group means that a generator exists, and we're just going to select a generator, doesn't matter which one, we select a generator just from the definition, and just reiterate to the reader that the order of A is n, just by definition of cyclic group. Okay. So now we know what A is, and we can use that in the reverse implication proof down here at the bottom. Let G equal A to the power j. Right. So now let's shift the burden of proof. We'll show that G is the desired element of order k. Uh-oh. But in addition to A being a surprise symbol, J was also a surprise symbol. So I have to look back at my napkin and ask myself, where did J come from? J came from this division that happened over here. J came from this unpacking of the observation that k divides n. So we need to put that ahead of my use of J as well. So since k divides n, there exists an integer j such that n is equal to k times j. So we're using the definition of divisible, right? We might even say by definition of divisible. Since k is divisible, since k divides n, there exists an integer j such that n is equal to kj. And then when we say let g equal a to the power j, now the reader knows that a refers to the generator, and j refers to the integer that we just brought into existence here when we made an appeal to the definition of divisibility. We'll show that g is the desired element of order k. And again, we do that in two parts. First, we show that g to the power k is equal to the identity. And that is where my napkin calculation comes in once again, right? The calculation that we did right here. Right? G to the power k is equal to a to the j to the power k, and that's equal to a to the power jk, and that's by properties of exponents. Let me catch up here so we have everything we need on the screen. So using properties of exponents, g to the k is equal to a to the jk. But then this is equal to a to the n by construction. So this is how we got our j in the first place, right? Is we made the observation that n must be equal to kj for some integer j. And so, actually, why don't we turn that around and say jk, so you don't have to also appeal to the commutative property of multiplication. Okay, so jk is equal to n by construction of j, right? By this equation up here at the top that defined j for us in the first place. But then we know a to the power n is equal to the identity, since the order of a is equal to n. Because a was a generator for my cyclic group of order n, we reminded the reader that the order of a was n up here on the top, and therefore a to the power n is equal to the identity. So now we've shown that g to the power k is equal to the identity element in my cyclic group. That must mean, therefore, the order of g is a factor of k, right? Remember, g to the k equals identity doesn't necessarily mean that the order of g is k, but it does mean that the order of g goes into k evenly, right? So we now need to show that the order of g is no less than k. So now that becomes my new burden of proof, right? And we can do that again by going back to our napkin and sort of expanding on this observation. If I take any smaller power, so indeed, if L is less than k, then let's do the calculation that's there. G to the power L is going to equal g to the is going to equal a to the power j to the power L, and that's going to equal a to the power jl, again by properties of exponents. Get us caught up here. If L is less than k, then g to the power L is a to the power jl. Whoops, need to get that L back up into the exponent. Don't want to be confusing. There we go. It's equal to a to the power jl. But we also know that jl is going to be less than jk. Right? If L is less than k, since j is positive, I can multiply on both sides of this inequality without reversing the inequality. So jl is less than jk. But if jl is less than jk and jk is equal to n, then we know that this is not equal to the identity. And the reason being is that since JL is less than N, and A has order N. All right, let's see if this actually is persuasive the way that I'm thinking that it is, right? So if I take a smaller power than the kth power of G, then the lth power of G is the jlth power of A, but JL is less than N. And so what I have is a power of A which is less than the nth power of A. And since the order of A is N, that means that no lesser power than the nth power of A is equal to the identity. Therefore, A to the jlth power is not the identity. So G to the lth power is not equal to the identity. And therefore, at the end of the day, thus, the order of G is not less than K, and hence is equal to K. So we sort of showed this in two pieces, and this is always the trickiest part about making arguments about order. Right? We first showed that the kth power of G is equal to the identity, and therefore the order of G is at least a factor of K. But what factor of K is it? we have to show that not only is the kth power the identity, but no smaller power than the kth power can be the identity. And we did that by picking a smaller power, raising g to that smaller power, and arguing that if it were the identity, then the order of a could not be n, right? Because only the nth power of a comes back around to the identity. And so this completes the backward implication for this theorem. Let's back up and talk about the forward implication. How are we going to show the forward implication? Which says that if there exists an element of order k, then k must be a divisor of n. We'll go back to our napkin here for a minute. So let's suppose that we have an element of order k. Let's call it h. Has order k. If h has order k, that means that h to the power k is equal to the identity, but that h to the L is not equal to the identity for L less than k. Right? No smaller power of h is equal to the identity. But on the other hand, because we have a cyclic group, right, h is going to be some power of our generator. So h is going to equal a to some power. I don't know what I want to call that power. Maybe we'll call it r. Okay. So this is because my group is cyclic. H is some power of this generator. And so h is equal to a to the r. So a to the rk is equal to the identity. Right? But this is a to the rk, right? By properties of exponents. And so this must mean a to the rk is the identity. Therefore, rk, let me say it this way, the order of a must divide rk. But the order of a, because a is a generator for my cyclic group, the order of a is the same as the order of my group. Right? N must divide rk. So now we have to figure out why it's the case that k must divide n, if n divides rk. If n divides rk, this means that there exists an integer, let's call it s, such that s times n is equal to r times k. And so we have this equation that relates so now these four different variables together, s, n, r, and k. And I somehow want to make the argument that k divides n. Well, that's not going to be easy to do unless I happen to know that r divides s. If r divides s, then we'll be in good shape. But I don't think there's a way that we can control for that. So I think the piece that we're not quite getting yet is we're not quite getting the second definition of order. Right? H had order k, which means its kth power was the identity, but that no smaller power was equal to the identity. And so I don't know that this is going to be the right way to go here. Well, maybe we can do it. So let's suppose for a moment that... Well, let me start writing up this part of the argument, and then we can sort of figure out where to go from there. So in my forward implication, if we're doing this with a direct proof, we would say assume there exists an element h in G having order k. We will show that k divides n. It might be a good idea for us to go back to our concrete example one more time. So assume that I have an element of order 25 in my group. How do I know that 25 must divide 500? And my element here we're thinking of as being like 20, like the integer 20, right? So when I raise this element to the 25th power, I get the identity. So how do I know that 25 divides 500? So let's see. Actually, I guess R is playing the role of 20 now. R is like my 20. So a to the 20 to the 25 equals the identity. And And so that must mean that n, 500, divides 25 times 20, right? But then somehow we also knew that 20 already was also a divisor of, yeah, I think is that the key here? It wasn't just that n divides rk, it's that we also needed to show, yeah, maybe this is how we have to do it. We want to claim that n is equal to rk. Actually, I'm not sure if that's true either. All right, I tell you what. What I'd like to do is I'd like to patch this proof up a little bit later on today. So TBA. My apologies for having to bail out on this one because I want to make sure we get an opportunity to talk a little bit about one more element on our agenda, which is the contention down here at the end. Well, I guess the second to the end, which is the statement that all subgroups of a cyclic group are themselves also cyclic. Let's do that before we wrap up today's stream, because I'm going to have to get going in about 10 minutes or so. So let's suppose that G is cyclic and H is a subgroup of G. Then I want to claim that H is cyclic as well. Right? So every subgroup of a cyclic group is also going to be cyclic. Can't guarantee that I'm going to have the time to do this proof justice either, but let's try and think about how we might do this by way of a concrete example. If I take, again, G is Z500, or maybe let's make it a little smaller. Let's just make it Z50 for the moment. And let's suppose that I have a subgroup of Z50. My subgroup has got to have the identity element in it. And it's going to have a bunch of other stuff. But let's suppose that I happen to know that inside of this subgroup Z50, one of the elements that I have in there is, let's say one of my elements is 20. And another one of the elements that I have in there is 35. Right. So suppose I know what a couple of the elements in my subgroup are. I want to know why it must be the case that H is actually cyclic, right? What is a generator for this H going to necessarily be? So 20 and 35 being a part of this subgroup means that any sum or difference of them, right, any product of them with themselves or with their inverses is also going to remain in H just by properties of subgroups. And therefore, 20 plus 35, which is 5, is going to be a part of this group. 20 plus 35 is going to be 5. So 5 belongs in this group. 20 minus 35 is 25 mod 50. 35 minus 20 is 15. And so 15 belongs to this group. But as soon as I know that 5 belongs to this group, I also know that 5 plus 5 is going to belong to this group, 10. And I also know that 25 plus 5 is going to belong to this group, that's 30. Right? And so what it looks like is happening here is the fact that 20 and 35 can generate together the number 5 will then guarantee that every power of 5 belongs in this subgroup as well. But it doesn't look like between 20 and 35 we can make any other numbers less than 5. We can't make a 1, a 2, a 3, or a 4, right? And we can't make any other number that's not a multiple of 5. And so kind of the observation that we're working on here is that if 20 and 35 are in H, then this means that all multiples of 5 must be in H. And what's the role that that 5 plays? It's the greatest common divisor of 20 and 35. Right? And so if I have a subgroup that contains those two elements, it must contain the entire cyclic subgroup generated by this greatest common divisor of 20 and 35. So the idea here is that the greatest common divisor is going to be our candidate for being the generator of the entire cyclic subgroup. And again, we're thinking of this at the level of just the integers right now. And of course, since every finite cyclic group is the same as the cyclic group mod n for some value of n, whatever n is the order of the cyclic group, then we should be able to draw this perfect analogy the way that we usually do. So I suppose what we would do then is try and make the argument more generally like this. Could we somehow take the GCD, the greatest common divisor, of all elements of G, of H, sorry, greatest common divisor of all elements of H, and then make that thing the generator of H? That's actually the general strategy for how this proof unfolds. But I'm getting too late into my stream today just to fill in all these details, so I'm going to make another apology for this one. Let's just do what we still have time for, which is this very last element, to show that if P is a prime number, then the group ZP, the additive group of integers mod P, is a simple group. It has no subgroups except for the ones that all groups have, the trivial subgroup and the entire group. So let's take a look at the proof for this. And I'm posing it as a corollary because it really is a corollary to the theorem that we have above here, which says that all subgroups of a cyclic group are cyclic, and also that the orders of all elements in a cyclic group have to be divisors of the order of the group. So with those two things in mind, let's try and write up a proof of this corollary. So an example of this corollary in action is if you give me a group like Z mod 7, 0, 1, 2, 3, 4, 5, 6, with addition mod 7, right? That the only subgroups of Z7 are the trivial subgroup, right, just 0, and the whole group itself. Let me just write Z7. Right? Just the trivial group and just the whole group. There's nothing in between. One of the reasons for that in Z7 is as soon as you give me one non-trivial element, like 4, for example, well, 4 turns out to be a generator for Z mod 7. It's a generator for Z mod 7 because it's relatively prime to 7. And because it's a generator, as soon as I have 4 in my subgroup, that means I have every power of 4, but the powers of 4 generate every single element in Z mod 7. So as soon as I have one of these non-trivial elements, I have absolutely all of them. Right? There's no way to have just some of them and not others. And so the logic might be as follows, that if H is a subgroup of G, of Z7, let's say, right? I'm going to stick with this example for a minute. Then we know for sure that H is cyclic, because Z7 is cyclic. Right? We know for sure that H is cyclic. So H is generated by some element B. Right? But we also know that B has an order which divides 7. And the only numbers that divide 7 are 1 or 7. Right? That's coming from our fantastic theorem. B has order 1 or it has order 7. If B has order 1, then this means that B is equal to the identity. And therefore, H would be the subgroup generated by the identity, which consists only of the identity. So H would be the trivial subgroup. But on the other hand, if B had order 7, then H, the set of all powers of B, would have to be the entire group. Right? Because if it has order 7, since the whole group has order 7, that means H is generating the whole group. So that's the napkin version of this proof. Let me just write that in a paragraph here, and we'll be through with our live stream for today. So this is a nice thing about corollaries, is that you do all the hard parts of the proof as part of the theorems that come before it. And the corollary is supposed to just be a quick hit afterwards to show why those theorems imply very quickly the result that we're trying to achieve here. So let H be a subgroup of ZP. By the previous theorem, we know that H is a cyclic subgroup. Right, so we're first of all drawing on the theorem that we saw just a moment ago. Right, so we know for sure that H is a cyclic subgroup. By definition of cyclic, this means there is an element B in H such that the cyclic subgroup generated by B is equal to H itself. And then our question was, what is the order of that element? Now we're invoking the previous theorem, called the fantastic theorem. The order of B is a divisor of P, P which is the order of the group. But since P is prime, this means that either B has order 1 or B has order P. After all, those are the only divisors of a prime number, itself and 1. And so there's two cases for us to check. Case 1, order 1. If B has order 1, then B is equal to the identity, and the cyclic subgroup generated by B is just the trivial subgroup. And so that must mean that H is the trivial subgroup, right? If B has order 1, then B is the identity element, and therefore H, which is the cyclic subgroup generated by B, must be the trivial subgroup. Case 2, order P. If B has order P, then the H, which is the cyclic subgroup generated by B, has P elements in it, right? So B is going to generate a subgroup that has P elements in it. However, there are only P elements in G to begin with, and hence H is equal to all of G. Is the entire group. Thus, we have shown that all subgroups of G are either trivial or the whole group. And the only thing I did that is not good here is I have a surprise symbol. My surprise symbol here is G. I accidentally forgot that we were being very explicit here about starting with the group Z mod P. So I'm just going to replace every instance where I said G here with Z mod P instead. Z mod P, Z mod P, recompile it. There we go. So there's our proof of this corollary. So it tells me that the cyclic groups of prime order are actually really boring. They're super valuable. They're so useful. We're going to see they probably are the best groups of all time, but they're really kind of dry because they don't have any interesting subgroups. Because if H is any arbitrarily chosen, maybe I'll add that to my first line, let H be an arbitrarily chosen subgroup of ZP, then we know for sure that subgroup will be cyclic by the previous theorem. And then by the fantastic theorem, we know that the order of its generator will be a divisor of the order of the group ZP. And the order of ZP is P. But being a divisor of a prime is where suddenly we get really boring. We know that the order of that element is either 1, in which case that element is the identity, and so it only generates the trivial subgroup, or the order is P, which means that its cyclic subgroup consists of all of the elements in the group, and therefore the subgroup is the whole thing. Let me just compile this one more time because I had a bit of a typo. And there we go. So here's what our proof ends up looking like. So that's going to wrap up our live stream for today. If you have questions on what we talked about, feel free to drop those into the Slack chat. We're going to have a quiz on this material tomorrow, and then we're going to move forward into a totally different kind of group. It's at the other end of the complexity spectrum from cyclic groups. This is the group of permutations. So I'm looking forward to working on those with you then.